Hi everyone, Mr. Lee here. In this video, we're going to go over the work energy theorem using calculus. Alright, let's begin. So let's first come off with the work energy theorem as we know it. We know that if work is being done to a system, that means the system will have a change in energy. Now we also said this change of energy is in the change of kinetic energy. So object could be have an increase in velocity or a decrease in velocity, aka a change in kinetic energy. Alright. Now, from there, we also went into what creates work, right? Because we went into the formula of work, which is force times the dot product of the displacement. And another way to write this is force cosine of theta of the displacement. Okay, so simply put, what this means is that if your force is parallel to the axis of motion or the displacement, work is done. Versus if the work is, if the force is perpendicular to the axis of motion or the displacement, work is not done. In fact, work would be zero. Okay, if it's 100% perpendicular. All right. So the reason why we want calculus to do this is, well, there's two requirements. Requirement number one: if the force is not constant, as in the force is changing, and oftentimes this comes in when we're talking about springs. Or two, if the direction of motion is not constant. Okay, so the first one, we can take a look at springs, and the second one is when we're talking about motion. So for example, this is for number two. If we were to talk about a object that slides down a ramp, right, the direction of motion is constant. Okay, it's constantly moving in the same axis. Versus if we were to do something like this, okay, where it's all shaped differently, right? So it's moving forward and then it slides down like this. Okay, so we have a changing motion. And so for scenario two, that's when we would use the calculus version. So let's come up with the calculus version of the equation. In the calculus version of the equation, delta E is equal to the work, which is equal to F dot product, the dr. Okay, so this is what's going to be showing up on your equation sheets. Now sometimes you might see me write this as work is equal to x initial, x final, where f dot dx. Okay, but just so you know, it's the same thing here, right? The r just means it could be, you know, from point A to point B. So you'll see me use either one of those versions. So let's go into what this equation means and why we need to use it. So we're going to use the scenario that I described before. All right. So if we have a object that is not on a smooth surface, like so, the direction of motion is constantly changing. So for example, if the object is here, it's moving in that direction, versus if the object is here, the object is moving in a different direction, right? And so what this dr tells us is how much or how the direction is changing. Okay, how the direction is changing. And more specifically, it's showing us a infinite amount of changing of directions. And so it looks at it from tiny little pieces. Okay, so we take a look at a snapshot of when the object is there, and we can, I'm going to do my best impression of another snapshot when it moves slightly forward, right, how that motion has changed, and if it moves slightly forward again, how that motion has changed, and if it moves slightly forward again, right? And so what you're looking at is over a infinite amount of possibilities as the object is going from here, and it's landing all the way down here. So we're taking an infinite amount of snapshots, and that's what the calculus tells us. And so if we were to come up with the equation, right, F dot dr, what this shows us is that the force along this infinite amount of motions, all right, those infinite amount of little snapshots from position 1 to position 2. Okay, from your initial to your final. So what is the work as it goes from the very, very top all the way to the very, very bottom, if you were to find it an infinite amount of times? well, they want to be infinite, right? Because there is a limit to how many times, but we like to use the word infinite. And so this dr is taking a tiny little look at these snapshots along the way. And the calculus really helps us with that. All right, let's try a practice problem. So let's say we're given a force, a function of a force where f of x is equal to kx to the fourth divided by 2, where k is a constant, and we'll just use the number 100. Okay, so what is the work done if this force goes from the initial position of 0 meters all the way to the final position of 2 meters? All right, so what this tells us is that we have this force, right, and that force is given us by this function, and this force is dependent on the location, right? So depending on the location of the object, a different force is happening. And so from here we can figure out how we can figure out the work based on the newly found equation. So let's set that up. So we know that work is equal to the integral of f dot, I'm going to use dx here, simply put, because we have x as the changing variable, where our initial position is 0 and our final position is 2. So we can rewrite this as 0 to 2, kx to the fourth divided by 2 dx, right? So this is the setup. At this point, I'm going to take out my k, bring it out in front because my k is a constant, and they told us that k is 100, but we didn't define that yet, so I'll leave it as k. We have x to the fourth divided by 2 dx, right? This 2 is also a constant, so I can actually bring that out as well. So we get k divided by 2 divided by, or excuse me, and we're going to integrate that from 0 to 2, x to the fourth dx. All right, so this is important. When we're doing the integrals, we want to make sure that the variable that we're integrating for is the only thing that we're integrating, and everything else we can pull out. All right, so we said that k was 100, so 100 divided by 2 from 0 to 2, x to the fourth dx, and at this point I have to use my integral rules. All right, so we get 100 divided by 2, which is 50, and let's integrate x to the fourth. So x to the fourth, we do the exponent plus 1, so 5 divided by that newly found exponent. So x to the fifth divided by 5, and we have to derive this from 0 to 2. So we get 50 times x to the fifth, so 2 to the power of 5 divided by 5 minus 0 to the 5 divided by 5. All right, and I'm going to bust out my calculator to see what this is equal to. All right, 50, so 2 to the fifth power gives us 32 divided by 5, minus 0 to the fifth power gives us 0, 0 divided by 5. Let's clean that up. We get 50 times 32 divided by 5, and 50 and 5, we can get 10 times 32, and we get a total of 320 joules as our final answer. So the work done was 320 joules along the path from 0 to 2 meters, given this function of a force of kx to the fourth divided by 2, where k is 100. All right, let's try another one. We're given this function of a force with respect to position as 20x minus 12x squared, and it is going from position of 0 meters to a position of 3 meters. What is the work done on this object, whatever this object is, from those 2 points? So in order to do that, we will have to come up with an integral from 0 to 3 meters, okay, of f, that should be a capital F, excuse me, of f of x dx. All right, so I'm gonna write in my function from 0 to 3 of 20x minus 12x squared dx. Okay, and at this point we're going to integrate these one by one. So what I mean by that is I want to integrate 20x and I want to integrate negative 12x squared individually. So let's see what I do here. I'm going to show you a little trick. So we're going to go from 0 to 3, 20x dx minus the integral from 0 to 3 of 12x squared dx. Okay, I just separated it individually. So if I were to integrate 20x from 0 to 3, I would get 20x, so this is the power of 1, so I'm going to add 1 to it, 20x squared divided by 2 from 0 to 3, minus the integral of 12x squared. So we're going to go up, your 2 exponent is going to go up by 1, so this will be, oh, before I do that, I'm going to take out my constant of 12, there we go, x squared dx, yeah, let's do it like that. Alright, so we get 20x squared divided by 2 from 0 to 3 minus 12. Alright, so the integral of x squared gives us x cubed divided by 3 from 0 to 3. Okay? Alright. Now, with this, we can find our integrals from those values of 0 to 3. And so 20x squared will be 23 squared divided by 2. Okay, and 0 in the numerator, which is because of 0, so I can put that in, minus 12, and this is 3 cubed divided by 3. Alright, so this gives us, let's see, I'm going to pull out my calculator. Okay, so we get 3 squared, which is 9, times 20, that gives us 180 divided by 2. So this gives us 90, minus 3 cubed gives us 27 divided by 3 gives us 9, times 12 gives us 108. All right, and 90 minus 108 gives us negative 18 joules. So what this tells us is that this object got energy taken away from it.